Welcome students in the feedback session of the second challenge in PV2X. We have asked you several questions. One was based on wafer-based silicon is so cheap that the other PV technologies are facing an enormous challenge to upscale production at the same rate to stay competitive in terms of the price per watt peak. So where does that leave the other PV technologies? Will these technologies ever be able to compete? Will there be a market for these other technologies when they reach maturity? So Giulio states, I think that in a short term the crystalline silicon will dominate the market, but in the middle and long term I bet for the thin film technology because it's very adaptable to any kind of surface. Optimum balance between cost efficiency and adaptability. So I agree with Giulio that indeed the current bulk volume market, it's very hard to compete with crystalline silicon. But of course the next generation applications of PV technology will have a lot of products which have different metrics than only being cost effective and cheap. And as you see over here, for instance, we already showed it before, the building integrated products in which you need different type of technologies like lightweight and flexibility, and there the new technologies will come in as well. So Christian Saldivar agrees and adds to that, the transportation of electricity is expensive and has energy losses. There is where I believe the other technologies like thin films will have their applications. Like make aesthetical improvements of thin film devices to use them into architectural design in buildings and houses. That way some of the electrical energy could be consumed in the same place where it is produced, having less losses of transportation. So again, here you see the example, but we also have some other examples like we showed in the OPV courses. So devices in which, like here you see, you can make any print you want and can get very artistical impressions. And this can be achieved with new technologies, which is much harder to achieve, of course, with a wafer technology. On the other hand, wafer technologies, we also have shown some examples where you have the imprint on the glass. So a lot of new generation of PV technologies are coming up. Bart Delvaux adds to that, not only energy transportation losses, but also the balance of system component cost can be reduced by thin film technology. Thin film, for instance, is cheaper to install because it does not need so much supporting structure as panels do. Furthermore, it can be incorporated in construction elements. Yeah. I also fully agree. You have to realize, for instance, I believe a number in Europe of something like 700 square kilometers of flat roofs exist, which are only designed to carry, for instance, 30 centimeters of snow. So glass modules cannot be integrated on these roofs. So there, a lightweight thin film product can use surfaces which now not can be utilized with solar energy technology. That's why AMAR M11 thinks that in the near future we'll see a boom of flexible solar cells based on this film PV technology, as they can be used in many creative ways. And here we see another example of how thin film technology can be integrated in very fancy, complex, three-dimensional geometric structures. We also asked the students, should we continue to pursue all these technologies? Should we focus all our attention on only crystalline silicon? So Sebastian misunderstands efficiency limit. It has been mentioned that the maximum theoretical efficiency for a single junction crystalline solar cell is 29.4%, and we are close to it. However, this is for that particular kind of solar cell. Also in this course has been discussed that technologies like gallium arsenide has achieved record efficiencies equal to 46%. This means that the theoretical maximum efficiency for other PV technologies is above 29.4%. Therefore, doing research on all these PV technologies will help to determine which technologies are better than others and also under which circumstances. Josué Andino also thinks that research is justified. Maybe in the future there will be a better, cheaper or powerful technology than crystalline silicon. The only way to find it is developing and researching with the other PV technologies. So Bart Delvaux agrees, because maybe nothing better or cheaper will be found, but there is no research. If there is no research, we will never know, of course. And I fully agree with that. Even there are still a lot of research questions in crystalline silicon. So we, for instance, can achieve very high efficiencies close to the theoretical limit, but it doesn't mean that we can produce this very cheaply in production. So in processing, there are still a lot of fundamental questions. And looking into other materials, maybe cheaper materials than silicon, it's still worthwhile. Over here you see the famous Schottky-Queisser limit, which we discussed. But it means that if you look at a single junction solar cell, you see that every band gap has its limit, and this limit is at maximum something like 33%. But it's more important to look like you need different materials. For instance, if you want to go beyond this limit in multi-junction stacks. And there are a lot of challenges, because in week 8 we have discussed that either using gallium arsenide, which is quite expensive, or using, for instance, perovskite materials on top of crystalline silicon still has challenges. One is too expensive, the other one is too unstable. So research for materials is still important, even also for the thin film products, which will be the next generation products, which we can cover every surface we want. There are still a lot of challenges, and of course we need research. And even if we don't find anything better, as the last student states, if you don't do the research, then you will never know. So I thank you for all the nice comments on the challenges of the second challenge of this PV2X MicroMasters, and I see you back soon in the exam of PV2X.